So, all right. So now we're going to talk about the preservation of quadratic invariants. Okay. By Runge-Kutta methods, and we already know that Runge-Kutta methods will preserve linear invariants. So let's consider the following kind of quadratic invariant. So we have a quadratic invariant, and what it basically means is that you want a property that for any solution of some initial value problem, you have the property that y of t transpose s of y of t is identically equal to the initial the quadratic invariant evaluated initial data, which is y0 transpose s y0, and you want this to be true for t greater than or equal to 0. Okay, where S is a non-zero symmetric d by d matrix. Okay. All right. So as you might expect, the discrete analog of the method preserving the quadratic invariant is the following. So in the discrete setting, so discrete time setting, right, you want a method which does the following, that yn plus 1 transpose s yn plus 1 is equal to yn transpose s yn, and this is true for n equals to 0, 1, and so on. Okay? All right. So let's try to state a theorem. It's like about the Runge-Kutta method, so it's like we're satisfied this. And as you might expect, this is very similar to what we had done before. So we'll see that there are actually a lot of similarities. Okay, so the theorem, as stated, is that suppose, okay, a Runge-Kutta method is applied to a differential equation which has a quadratic invariant. So let's just say star, right, with a quadratic invariant. Right, okay, so let's suppose we have this. Then if the famous M matrix associated with this Runge-Kutta method is identically 0, right, then the method has satisfied sort of this discrete version of the preservation of quadratic invariants. So let's call that star star. And is consistent with the invariant. Okay, so let's see how we do this. Okay, so let's try to prove this. Okay, so you have again the internal stages. It's like, right, you have the internal stages of the RK method, denoted by y1 to ys, right? And then you can have rho be the rho k, it's like be the vector field associated this. So this is f at tn plus ckh. right? And then and sort of y k. Okay. So you sort of do the obvious thing, right? You write down yn plus 1 transpose s yn plus 1. You write it as this sort of Runge-Kutta method, right? Yn plus h times the sum from k equals to 1 to s of bk rho k transpose s yn plus h sum from k equals 1 to s of bk rho, well, I guess the index here is L, right? L, L, L. Okay. Yes, and then we can take out the part of this, which was the original quadratic invariant. So this is yn transpose syn, right? Plus then the cross term, right? So sum from k equals 1 to s of bk rho k transpose s yn plus yn transpose s sum from L equals to 1 to s of bl rho L, right? Plus h squared sum from k equals 1 to s, sum from L equals to 1 to s of bk bl rho k transpose s rho L. Okay. Okay. And then if you have, you can rewrite the Runge-Kutta method, right, in the following way. Yn is equal to yk minus h, the sum from L equals to 1 to s. Okay. AKL, right, rho L. Okay. So normally I've written this as yk is equal to yn plus this sum, but I've just sort of replaced it and written yn in this way. And if you recall, it's like when we were trying to prove the condition for simplicity, the goal here is to replace the yn you see here in these terms, right, with these other terms here. Okay. So what happens then is that, right, so we'll look at these terms. So this implies that rho k transpose syn is equal to rho k transpose s yk, right, minus h sum from L equals to 1 to s of akl rho k transpose s s rho L. This is from k equals to 1 to s. Okay. All right. And then, so the other thing you have to do of course, is that you have to use the fact that you're applying this to a differential equation which has a quadratic invariant. So I need to use that fact somewhere. Okay, so I need to differentiate the condition that y of t, so let's write this, little y of t transpose s y of t, right, is identically equal to y0 transpose s of y0. Okay? And you differentiate that clearly, of course, with respect to time. It's like, and then that gives you a condition, if you will, on the differential equation. Okay, so this tells you that 0 is equal to y transpose t s y prime t. Okay, and this is equal to, yeah, and so here, of course, we use the fact that S is symmetric, right? Yeah, so we use the fact that S is symmetric here, because otherwise normally you would have two different terms. When you do the derivative, it's like, and you use the product rule. Okay? All right, so anyway, so you get this is equal to y transpose t s f of t y of t. Okay, and this is true for t greater than or equal to 0. Okay, so this is a condition which we're going to use, and you can see where that shows up. It shows up with these terms here, right? So this term looks like this term here. It's the vector field at the point yk. You know, it's like, and paired, it's like, but with the symmetric matrix as the mass matrix, if you will. Okay. So, so this implies, if you will, that you know, how should I say it? Right, so that yk transpose s rho k. Right, so this is equal to 0, but this is also equal to rho k transpose s yk. Okay, so anyway, so these terms vanish is the main point. So you're just left with, so this implies that rho k transpose s yn, right, is equal to minus h, the sum from L equals 1 to s of akl rho k transpose s rho L. Okay, all right. And then you can use a similar argument to deal with this other term here. Okay. You can also show that, yeah, so you take the b's out, if you will, it's like, and you get something here. All right, so this also, okay, so where was I? Yep, so you have this, and you can also show that right, yeah, you can show this term here, right, yn transpose s rho L is equal to minus h sum from k equals 1 to s of a lk rho k transpose s rho L. Okay, all right, so you can deal with these two terms. These two terms already have this rho k transpose s rho L term. All right, so, all right. So let me try to just erase this for now. right? So this was the condition that, right, yn plus 1 transpose s yn plus 1 is this, right? Okay, so I'm going to leave this here and I'm going to copy it out. So yn plus 1 transpose s yn plus 1 is equal to yn transpose s yn, yeah, plus these terms. Okay, so minus h squared, right? So I'm replacing this and this terms with these two. Okay, minus h squared sum over k equals 1 to s, sum over L equals 1 to s of bk, right? Because so this is just for each of these terms, they're all multiplied by bk, so I have bk multiplied into the akl terms, akl plus bl multiplied, the bl multiplied into alk, alk minus bkbl, the bkbls come from here. All of them have the same term, rho k transpose s rho l, rho k transpose s rho l. Okay. And of course, this is nothing more than your coefficients of the M matrix. So this is yn transpose syn plus h squared, the sum from k equals 1 to s, the sum from L equals 1 to s of m kl rho k transpose s rho l. Okay, all right. And so clearly, right, if the sort of the famous M matrix is identically 0, right, then this term vanishes and you're just left with this. So clearly then, if MKL is identically 0, right, that yn plus 1 transpose syn plus 1 is just yn transpose syn, which implies that you conserve the quadratic invariant, which is what we wanted to show. Right? Okay, so let me just stop here for now.